Hey everyone, we're going to use the principle of mathematical induction to prove that the sum of 2i minus 1, that quantity squared from I equals 1 to n, equals n times n minus 1 times n plus 1, all divided by 3. And this is for all positive integers. So this means for all. Back upside down A. If we look at this, let's expand this and just see what we have here. If you plug in 1 for this I here, you're going to get 2 times 1 minus 1 is 1, 1 squared is 1. And this is a summation, so we're adding this. When you plug in 2, 2 times 2 is 4, minus 1 is 3, square it, you get 9. And let's do one more. You plug in 3, you're going to get 6 minus 1 is 5, and square it, that's 25. And then you keep going, and the last one you want to plug in is n. So this would be 2n minus 1 squared. Now basically when you see this just means odd numbers. So basically this is the sum of the square of the odd positive integers. And this would be odd, and this is also odd, the way it's written. If you ever see just 2n, that means it's even, because it's a multiple of 2. So that's what that says. Now all we have to do is prove this. So the first step we're going to do is show that it's true for n equals 1. So just plug in 1 here, and we know that equals 1. We already did that. And then plug in 1 in your n here. So this would be 1, 2 times 1 minus 1, 2 times 1 plus 1 divided by 3. So this equals 1, and this is 1, and this is 3. So this is 3 divided, that's just 1 times 1. So 3 divided by 3 is 1, and so they check out. So 1 equals 1, and that's supposed to be your first term. So we want to show that it works for n equals 2, n equals 3, and n equals 4, and so forth. And so the way to do that, instead of having to plug them all in all the time, is we're going to show that it works for assume. So we're going to assume it is true for n equals k. And we're going to write this out. You can just leave it like this. I like to write it out. So we had 1 plus 9 plus 25. The next one would have been 49. You only need to write 3. You need to write 3 terms, especially if your first term is a 1. So always try to practice writing at least 3 terms. And then plug in 1 n for this. So this is going to be 2n minus 1 squared. We don't want n. We're going to assume that n is k. So I'll change this to k. Sorry about that. So this is 2k minus 1 equals, now change all those n's here to k's. 2k minus 1 and 2k plus 1. All divided by 3. Now, that's our assumption. And our last part we're going to have to do is actually prove it. So we're going to prove that it works for n equals k plus 1. So that means your next terms, whatever they might be. So what you do is you copy the first part down, 1 plus 9 plus 25 plus dot 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 plus 2k minus 1. Now the next term is the one that follows this one. So basically the next term is going to be 2k plus 1. You can do it either one or two ways. You can just take your 2k minus 1 and plug in k plus 1. And that's going to give you your 2k plus 1. Or you can just look and see that since this is linear, this slope is 2, we're just adding 2. So the next term after this would be 2k plus 3. The next term would be 2k plus 5. So it's just all your next odd terms. Now this part, we're going to write this as the next term would be k plus 1. The next term for this would be 2k plus 1. Next term for this one would be 2k plus 3. All I'm doing is adding 2 to my constant here. Divide it by 3. All right, following that, we got to prove it. So we already know what this equals. So this part here is on our assumption line. This equals this. So copy that down. And then copy your new term you're adding, or your next term. And that should equal the sum of everything, including the new term. All divided by 3. And before we move on to the next slide, the one thing we need to do is have a common denominator for this left-hand side. So I want a 3 to be the common denominator, and to put a 3 there, we have to also put it there. All right, so that gives us the common denominator. Now, on the next slide, I'm going to clean this up a little bit. So basically what we have is k times 2k minus 1 times 2k plus 1 plus 3 times 2k plus 1 squared all over 3 equals k plus 1 times 2k plus 1 times 2k plus 3, all divided by 3. Now, since we have that, instead of just cleaning all this up at the top, let's notice that we want the left-hand side to equal the right-hand side. And we're going to get a cube term in here if we're not careful. So what we want to do, no, maybe not. Okay, but anyway, we have a 2k plus 1 here. And we have one here and one here. So I'm taking these as two different terms here. And I'm going to factor out a 2k plus 1. So I get a 2k plus 1. And if I factor that out, I'm left with, on this part, I'm left with k times 2k minus 1. And for this part, I'm left with 3 times 2k plus 1, because I'm factoring out this 2k plus 1. Now all we need to do is simplify. We have 2k plus 1. And let's fix that. This is 2k squared minus k plus 6k plus 3. So I'm going to add those two up. So 2k plus 1 times 2k squared plus, that should be a k, plus 5k plus 3. Now we have to make it look like this side here. So I'm going to factor, we have 2k plus 1. I'm going to factor this trinomial. So I have a 2k and a k. Need a plus and plus. I need a 3 and a 1. And what I tend to do is I look up here and kind of cheat a little bit. So we need a k plus 1 and a 2k plus 3. And then I check it. So I check and make sure when I FOIL it back. So we do have our 2k squared. And this is 2k plus 3k equals your 5k. And of course 3 times 1 is 3. So here we have it. This is the same as this. If you want to rearrange it, you could, but you don't need to. So basically, just looking at this, this equals that, and you did your proof. So we're good to go, and that's it. Thank you. Have a nice day. Bye-bye.